All right, this is a big day in calculus. You are getting your introduction to integration. Basically, the first half of this calculus course is related to derivatives, and the second half is related to integration. So it's a big day. I'm sure you're celebrating. The integral, as you may or may not know, is this beautiful S-like symbol that tells us we're going to integrate. And there's going to be a very, very, very large amount of information that comes with the integral. Today is just an intro and showing you a few easy techniques. So let's begin with a little vocabulary. This will be the first problem we work with, but before we get there, let's take a look at this problem. Imagine you were just seeing the black ink. It's basically saying, let's take the integral from -2 to 7 of 3x squared plus sine of x. The equation that you're working with in a case like this is called the integrand, and these are called the limits of integration. They're kind of like a beginning and an ending point, you'll soon see. And I'm not sure the name for this dx, but I'll tell you it's very informative, and in the beginning it'll seem not necessary, and you'll change your mind about that someday. So let's move on to this very first problem. And for today, we're going to work with a graph. And I'll be popping this up here quite a bit, and I'll have to take it down at times. But there's our graph. It's a graph of f of x, and every problem we work with today is going to work with this graph. Since this is kind of a piecewise graph, I can't really replace it with an equation in the integrand, so I just name it f of x. And here's what problem 1 is telling us to do. It's saying start at x equals 3 and end at x equals 6, travel along the x-axis, and trap area underneath f of x. So what that means is I would start at 3, I would go all the way along the x-axis until I got to 6. And what I would be doing is I would be thinking about the area that gets trapped between the function and the x-axis. That's why this dx tells me area trapped along the x-axis, and I move along the x-axis. So in a case like this, I can just count the squares. 1, 2, 3, 4, 5, 6. That tells me my answer is 6. There's another way. If I can't count the squares, I can take a look at that and I can say, you know what? That's a rectangle that is 3 units long by 2 units tall, and 3 times 2 is 6. So the answer to that integral is 6, but we're going to do integrals that look similar to that, and you're going to have a little bit deeper thinking. Okay, I've now changed this setup to look at problem 2. Pretty darn similar, but we have a change of thinking now. We're starting at 4 and we're ending at 2. Well, that's a subtle change, but that means we start here and we're traveling in the negative direction to get to 2. I'm still traveling along the x-axis, and I'm finding area trapped between f of x and the x-axis. So there is my trapped area, and so you would think that the answer is 4 because you count 4 boxes, or you have a square that's 2 by 2. But it's a little bit more intricate than that. In a case like this, we were traveling in the negative direction, so that's kind of like a -2. My region was above the x-axis, so that's kind of like a +2. Thus, the answer is -4. So paying attention to the direction of your limits of integration is a big deal. Okay, I've set up for a new example. This one takes your direction of travel and another factor into account. So I'm starting at 0, and I'm going to -4. So I start here, and I'm ending here. If I wanted to draw this geometric figure, it would look something like this. Your friend, the trapezoid. Now, as I'm traveling from 0 to -4, I realize I'm traveling in a negative direction, but also the region that I'm trapping between the function and the x-axis is in negative territory. So I kind of think of it as this is negative and that's negative. So you know from 6th grade that a negative times a negative is a positive. So I know my final answer is going to be positive, and I can either count the squares, 1, 2, 3, 4, 5, 5.5, 6, or I can use the trapezoid formula. That's a 2, that's a 4, that's a 2. And for me, the trapezoid formula says take that perpendicular piece and multiply it by the average of those two parallel pieces, which is 2 times 3, which is 6. So now my answer is positive 6, but only because I was traveling in the negative direction and the region was trapped in the negative or below the x-axis. So you'll notice that our answers are always related to trapped area, but the plus or the minus sign has to be thought of in terms of direction of travel and whether the region is above or below the x-axis. Okay, here's a nifty one. We're starting our lower limit of integration at -2, and we're traveling all the way to 2. So what I'm ending up with is this region down here, as well as this region up here. And what you'll notice is that in this case, it's very symmetric. What I have is a travel to the right the whole way, a certain amount of area below the x-axis, a certain amount of area above the x-axis. But because of this function, this region and this region have the same amount of area. So it's a negative something and a positive something. My final answer is going to be 0. If you really wanted to be picky, what you have is a very bad triangle plus another triangle, and in this case that would be a 2 by 2 triangle, and I'd still get my 0. So you can always work it out if you feel like it, but when you spot symmetry like that, don't be afraid to use it to make your problem quicker. Okay, I've set up one final example, and you'll notice a new character here. We have a coefficient on our integrand. So one thing you're allowed to do, you don't have to do this, but in a case like this, definitely a smart idea. You can take your coefficient and just put it right out in front, as long as you don't forget about it, which is easy to do. So that 3 is out in front. It's kind of like a factoring, although factoring is not the right word to use there. So I'm allowed to now just let that sit and just think about this, the integral. I'm going from 5 to -2, so I must notice that I'm traveling in the negative direction. I have to remember that. And if I start at 5 and I travel to -2, I notice that I've got this nice rectangular piece. It's a 3 by 2. And then as I move forward, this region, which we've already discussed, has a positive and a negative triangle that are of equal value, so I don't have to really consider much because these two values will end up adding to 0. In fact, what I'd like to do is make this a little tougher, and let's just say I'm going to stop at -1. Okay? So now we won't have this advantage of the symmetry because this triangular piece is more weighty than that triangular piece. So we have to keep that in mind during our calculation. So the way I would look at this is I would call this rectangular unit six units. Then I would look at this triangular unit and I would call that a 2 by 2 triangle for 2 square units, or 1 plus a half plus a half, but that would count for 2 units. And then this little piece is a 1 by 1 triangle, and that would count for 1 unit of area. But remember, I have to think of direction of travel. I'm traveling in the negative direction, and I have positive territory being trapped, so that's going to count as a -6. This is going to count as a -2, and this is going to actually count as a +1 because I'm traveling in the negative direction and the region is trapped below the x-axis. So when I combine all of this together, I get a -7. So what I have is 3 times -7, or an answer of -21, because that 3, which I moved to the outside earlier, has to still come into play for the final answer. So that's kind of a doozy of a final question, but it shows you all the moving parts working together. Hope you enjoyed your introduction to integration.